a bit differently. I want to tell you a story about how we started working together to make rodent functional MRI better, how your contribution matters, and how you can use that framework for working and bring it to your own communities, because I assume not everyone is interested in rodent fMRI. We're all doing different aspects of imaging. And this is a template for working together that has worked very well for us. And I would like to share that with you. I'd like to start by talking about the explosion of the concept of brain connectome as the disorder mechanisms. This is something that happened in humans. It's a development based on functional MRI, where you start looking at task-free activity and see how networks in the brain work with one another, and that can also be used to study pathology. This is one of my favorite examples from the literature growing into science, where they actually looked at task-free fMRI activity in healthy carriers of a risk allele for developing Alzheimer's disease down the line. And what they do show in panel B is that there's already significant differences in a part of the brain, which is the hippocampus, which is relevant for Alzheimer's disease, already in people who are at risk of developing Alzheimer's disease 40 years before the disease onset. And I find that really amazing. I'm not the only one, because working together in MRI has been a thing, and a number of very large projects have started aggregating mass amount of human MRI data, the most famous ones being the Human Connectome Project, UK Biobank, but you also have specific ones for brain disorders like the Alzheimer's disease neuroimaging initiatives and Nimega. And if you read the human imaging literature, these data sets are all over the place, being reused constantly to develop new ideas, to test models, and so on. In comparison, working with animals, we are a very niche thing. This is, well, now it's no longer updated, but in all the way to 2019, we looked at the number of publications per year in animal functional MRI. And so you can see that it has been growing, but overall, on a good year, you can expect maybe 100 publications, or you could expect at the time 100 publications about animal functional MRI, whereas for humans, you'd expect 1,000 publications a month. So you see there's a big difference. But I think our community has the potential to deliver information that is not available, that's missing in the human literature. Here, this is one example from our own work, where we looked at a mouse model for Alzheimer's disease. On the left-hand side, what you see is on top, the places where we expect from the literature where the pathology would set in humans. And then at the bottom, you see how our mice are affected with brain function in the early stages of the pathology with the matching histology. And you can use that information, you can build on it, and you can do all sorts of manipulations that are just not possible in humans to learn about the phenomena. So I think we have a potential to deliver something that's impactful. But for everyone who knows, and those who don't know as well, fMRI is challenging. Because MRI is fundamentally insensitive, we always work at the detection thresholds. It's an indirect physiological measurement of what we're interested. It's confounded by noise sources. It has a complex pre-processing and difficult interpretation. Trying to do it in rodents is even harder. You have to work with maintaining the animal physiology. You have questions about how to restrain the animals. The stress that you can induce, you work with a smaller brain, so that also puts strains on the signal to noise ratio. And then we are fundamentally tinkerers. So whereas people doing human MRI would rely on vendors providing machines and coils and everything, we tend to work with a large range of magnetic fields, much larger than humans. And then sometimes we also like to build our own platforms. So that means that we each work with very different tools in the end, and that impact the results. I was at the very start of the functional MRI, or the task-free functional MRI acquisitions in rodents. And at the time, we all got somewhat different results. And then we were asking ourselves at meetings, why? Why don't our results correspond to one another? So what I did, and this is actually the second iterations, but what I did is I called all the people that I knew in the community and I said, let's try to address that question. Let's pull our data and look at how they compare. Now, I'm going to talk about the second iteration of the study, which is much larger. In the end, we have 200 collaborators from 20 countries providing 82 resting state task-free fMRI datasets, each with data from 10 rats. So that's overall about 800 scans that we got. This is a map to show you where all the collaborators are. And I'm quite happy that we hit quite a number of places, and not just Europe and not just Germany, but it really is an international effort with labs from Canada, the US, Mexico, all the way to China, Japan, and Australia. This is a very brief summary of how diverse the data is. So I express it in terms of pie charts where we have different sexes that are being represented, different rat strains, different restraining methods, and then different field strength. Also, just for you to grasp a small aspect of the challenge that I had doing the processing, here I show at the bottom 3 different representative images, well, quote unquote representative images of MRI acquisitions that I got and how they all vary in terms of geometric distortions, but also signal to noise and quality. And I have to say that this work predates Marcus's present work on his quality control toolbox, so we couldn't use his toolbox. But going forward, this is something that we are now running as a standard. I don't want to bore you with all the nitty-gritty. I want to get through with you with the major concepts, what's really important. And so this is a plot actually Marcus showed earlier. The thing I want you to understand about this plot, every dot represents a single rat that has been provided. And then we divide the plot in 4 different categories, but there's basically one where we want all of our scans to be in, which is this bottom right quadrant of the plot. There are reasons for it, but basically the scans that are in this part of the plot are the ones that look like what we would expect. I show a representative image here on the slide. So if you were to pick up a random protocol from the internet and you were to apply it, you would have statistically, you would have about 30 to 40% good scans that fall in that category. And then between 60 to 70% of scans that would actually not pass this quality control measure, that you would have to discard or that do not contain any meaningful biological information that you can use for your study. And so we wanted to improve that. So we all sat together and we asked ourselves, how can we make a protocol better? And we looked at what made the scans in that quadrant different from the others. And so based on that, we designed a protocol. We sent that protocol back to everyone's lab. And then we got these new acquisitions with a standardized protocol. And in that standardized protocol, now we have about 70% good scans that are falling into the lower right quadrant of the plot. So what that means is, instead, if you want to do task-free rat fMRI, you could either pick a random protocol online and pray that it works, or you can try to follow ours. And it's designed in such a way that it can run on everyone's machine. And then you would have much better odds at getting good data, and that also includes from labs that actually were starting in the field, so that never had experience with rat fMRI acquisitions in the past. So if you're a beginner, I strongly encourage you to follow our protocol. But beyond that, this is also a project that's about promoting open science and good scientific practice. So we've pre-registered the study. The software that we use is different from the one Marcus presented earlier, but it's also an open source software that is pretty robust. We make all the data and code available for reuse, and then we also provide detailed information about quality control. And I think this is also something that we want to push forward in our community to show that our data can reach better standards. But as I said, this is a framework. And so now we're actually working on spin-off mass collaborative projects. So I currently have a project running where we're looking at awake fMRI. So this is a subset of fMRI that is using awake rats and mice. This is much harder. So this is ongoing and should be completed sometimes this year. We're also comparing different pre-processing pipeline. So I'm sending the same data set to different labs and asking them to process it their ways. But we're also moving on beyond the fMRI. So we're talking about brain spectroscopy, and this is a collaboration with Toronto and EPFL in Switzerland. But I'm also on the lookout for next big projects. And if you have some ideas, my email is very easy to find. Just drop me an email and we can talk about it. With this, I think science is a great thing, but what I really like about it is all the friends that we make along the way. And this is my list of collaborators. Many of them now I call my friends. Some of you are in this meeting at the moment. I'm very proud. I'm always very happy when I present. And then I have my friends who are in the meeting with me. I feel surrounded by friends, and this is a very good feeling. I have to thank a couple of people. So both two Gabriels and Mala Chakravarti from the Douglas Hospital in Montreal, and then Andy Hess for kicking my butt to get this project running. And I am looking forward to having some questions.